All right, good day, everyone. Then I'd like to welcome you all to the Biomechanics Challenge finals of 2023. We've had quite some participants, and all the participants have been working very hard in the last 2 weeks, or actually last 3 weeks, to come up with the best solutions to the problem that we've created for them. Firstly, I'd like to thank all of you for participating, for putting in all the hard work. We were astonished by the stuff that you guys send in, and we're really thrilled that you guys took the time to do this. Also, thanks Maria and the rest of the organizing people for making this possible, and of course the judges, who I'll be calling in a minute, for their help and assistance and their expertise. I would like to start with a quick recap of the case study. Now, I know you've been working all really hard on this, but there are also some viewers who didn't participate, so I'd like to go over it quickly. We captured a lot of data on cross-country skiers, and we've asked our participants to come up with a performance parameter. We did these measurements at the Val di Fiemme cross-country skiing course, which will be the host venue for the 2026 Winter Olympics. So we did some measurements with our Xsense suit, and we got some full body motion capture. Additional to that, we also got some GPS data, some frontal pictures of each of the athletes, an area picture of the map of the track. We got a data sheet where all the information was about the athletes that was needed, and we had some weather data, which might or might not be interesting. So we've created some mandatory project outputs for our students. The first one was the performance parameter. This was the main goal of the challenge. Now, to come up with a performance parameter, we asked them to assess the smoothness of the movement, the coordination, and the balance of the cross-country skiers. Also, we asked them to create a power output of the upper body versus the lower body, and to assess the adopted strategies and the track. So altogether, this will give a performance parameter on which they can score the level of the athletes that have been measured. Now, they had to clarify and justify what methods, assumptions, and everything they used. They had to rank 8 athletes with this performance parameter, and they should have made a mathematical method that describes the performance parameter. And it would be nice if they also had an automatic generated performance parameter per trial and automatically detected ski cycles. Now, if that wasn't enough yet, we also had some optional outputs, namely to calculate the friction coefficient of the snow and to reconstruct the ski slope in 3D. We had quite some turn-ins, some submissions of awesome reports, and our esteemed jury committee has gone through them all and selected the 8 finalists that will today be presenting their work for them. After the presentation of their work, they will again come together and determine who was the best of this year. All right, so ready for the finals. We're going to start with Team Monash. Then we'll be going to Biomechanics, Team Salzburg, SkiSense Innovations, MHMU Twente, York Biomechanics Team, Kinetic Crew, and Brockworth Filter. This is it's not really a random order, but it's not on order of skill or assessment. It's on order of time zone. So Team Monash is joining us from Malaysia. It's currently evening for them. So I would like to give them the floor to start.
So, hi everyone. We are Team Monash from Monash University. I'm Chamalka, and I will be presenting our work for this year's Biomechanics Challenge. So our focus this year was on cross-country skiing, which is quite a demanding endurance sport, and athletes need to have good physiological and tactical abilities coupled with their level of skill. So there are two main skiing techniques, moving from high power generation to high speed generation. But for our analysis, we mainly consider the classical skiing technique. So the primary objective of this year's challenge was to determine the performance level of 4 unranked skiers. We started off with a literature search, and we found a series of biomechanical quantities that can describe a skier's motion and could be used to classify their performance. So we looked at cycle, center of mass, and angular kinematics, along with power and their skiing strategies as well. So moving on to the methods. The first thing we looked at was to identify a ski cycle, which is the distance between two subsequent pole contacts. So the pole contacts themselves were identified using the right-hand acceleration. The pole contact occurs at a minimum after each peak within about 2 to 5 frames from that peak. And this is shown here on the plot with the red color cross. The peaks themselves were identified as having values at least 65% from the maximum and being 680 milliseconds apart. And the data was filtered using a high-pass filter with a cutoff frequency of 20 hertz. So once we were able to denote every ski cycle, we then could find the biomechanical quantities per cycle. So we started off with the cycle kinematics. So what we did was we considered 5 non-consecutive cycles towards the start and before the end of each trial. And we assumed that this would be roughly representative of the motion. Cycle length was found by integrating the sternum velocity per cycle, and that coupled with the cycle time gave us the average ski velocity. Next was the center of mass kinematics. So the center of mass range was in essence the difference between the maximum and minimum center of mass displacement in the anterior-posterior, mediolateral, and vertical directions. Now the mediolateral center of mass range could show balance and smoothness of movement, while the anterior-posterior and vertical could show an economical movement or even movement efficiency. Next were the angular kinematics. So this again, we looked at the joint range of motion, which is the difference between the max and min joint angles per cycle. And we considered the hip, knee, and the elbow, which were the primary contributors in skiing motion. Following this was power. So for power, we considered the potential and kinetic energy, and we looked at the total power output of the skier. We assumed that the total power generated or the total power output would be produced as a result of being able to overcome any frictional or drag forces. Similarly, for ski velocity, the average speed achieved per cycle would be after overcoming any frictional forces. So we did not consider friction in our calculations. And finally was the strategy, which was observed visually, but this was not done for just 5 or 10 trial cycles, but rather for the entire ski run. So after we at least had the biomechanical parameters, we then went into performing a statistical analysis. And this was mainly to assess the rank and performance of the ranked skiers. So we started off by testing for normality, and this was done using a Shapiro-Wilk test, which revealed a non-parametric distribution. Then came the Kruskal-Wallis-Edge test, which finds if a statistically significant difference exists between each of these performance parameters amongst the ranked skiers. And that was followed up by a post-hoc Mann-Whitney test, which finds the extent of this difference or the difference between each individual ranked skier. We also tabulated the descriptives of the ranked and unranked skiers and used the confidence interval of the ranked skiers to actually evaluate the performance of the unranked skiers. So, for example, if we had ski velocity of a beginner, the confidence interval would generalize this to a population and give us a range in which a beginner level ski velocity would lie. So we could compare the biomechanical quantities of the unranked skiers with these confidence intervals and determine the rank of each performance parameter, where the trend in the performance parameter would decide the final rank of that skier. And moving on to the results. So we tended to observe in general that experienced skiers produced a larger cycle length, lower cycle time, and a higher ski velocity. They tended to have a more anterior center of mass position, which shows a more economical or efficient movement. and they had less mediolateral center of mass deviation, meaning they had good coordination and balance and produced a smoother motion per cycle. They were also seen to generate more power and had a larger joint range of motion in overall. By looking at the strategies used, we noticed that experienced skiers tended to stick to one strategy, usually double pole, while other skiers tended to shuffle or use a range of strategies. So from this, we determined the rank of the 4 unknown skiers. 2 of the skiers were beginners, 1 was intermediate, and 1 was an advanced skier. So it was observed that a skier could display certain performance characteristics of a different rank skier. And what I mean by this is that, for example, if you had a beginner, he could display a higher ski velocity, which would be characteristic of an advanced skier, but have poor balance, coordination, or power generation. So we cannot just consider one single biomechanical parameter to evaluate their performance. Rather, we have to consider all these performance parameters together as a whole to understand the performance or the rank of a skier. Now, our study did have a few limitations. One was the small sample size, which affected our statistical analysis. And we only considered 5 cycles at the start and at the end. And we did not consider cycles in the middle of the motion. So it may not actually be representative of the entire ski trial. And we excluded any frictional forces in our calculations. So to conclude, we noticed that more experienced skiers tend to use specialized skiing techniques. They had more power and they tended to stick to a single strategy. All performance parameters together have to be considered to assess the rank of a skier and not just a single standalone parameter. And finally, performance classification in itself is quite useful because it can be used to develop targeted training programs that could enhance a skier's performance and even reduce the risk of injury. So these are some of the references we used in our presentation slides. And that's it. Thank you.
All right, thanks a lot for your presentation. I'd like to give the word to the jury committee. Do you guys have any questions?
I'll start. Your last point in your discussion there was that this information could be used to design like training programs. If you were a coach or even a clinician that doesn't have like the statistical knowledge that you do as a researcher, how could or would you use this data without that background information and context?
Okay. So as a coach who didn't have the knowledge, they would actually have to consult probably a person who does have some of this knowledge, and then they can find ways of assessing each of these parameters through normal skiing and finding ways of categorizing each parameter or ranking these parameters and looking for these parameters in a normal ski trial and trying to use these to evaluate how a person performs, and then comparing this with maybe an advanced skier, and then evaluating or rather informing them of how they could improve their technique or their ski style, for example. Does that answer your question?
All right, thanks. I see Daniel also. Yeah, go ahead.
Sorry, just a short question. Some minor detail maybe, but looking at the power data you got or the values which you had, would you say they are reasonable compared to other sports like cycling or so?
Sorry, the power data, is it?
Yeah. The values you achieved in the table.
They would be reasonable, yes, especially for the elite skiers because they do generate quite a lot of power and they are trained athletes. We haven't compared this data with other sports like cycling, so I can't give you an exact answer on that.
Okay, but thank you, yeah.
All right, Andrea, I also see your video. Do you want to ask a question?
Yeah, I have a kind of a question about the cycle selection. You mentioned that you selected a few cycles, but then you said in the limitation there were not so many cycles. So I'm wondering why you choose to select like only few cycles and you didn't take like the average of a few consecutive cycles to get like a a variability within every cycle or something like that. Can you please expand on
Yes.
that?
So there were actually quite a number of cycles per trial, and we didn't have time to consider every single cycle. So we were trying to look for a way to generalize the ski trial. And what we did was we considered a few cycles at the start and a few cycles at the end. Why we didn't consider consecutive cycles is because they would have been too similar and they wouldn't have been representative of that end of a region. But by considering non-consecutive cycles that were apart from each other, we could rather generalize this to that portion of skiing. So we considered the start, we considered before the end, and we assumed it would be generalizable. But of course, it is a limitation because we did not consider the entire trial.
Then it is time for Biomechanics. With their title, Ixen's Biomechanics Challenge Report, Performance Evaluation of Double Polling Technique in Cross-Country Skiing Athletes.
So, hello everyone. First, allow me to introduce ourselves. We are Team Biomechanics from Başşehir University of Turkey. And thank you very much for allowing us to be part of this very wonderful event. It's been really intense for us. We're really excited. And as you can see from our title, we clearly focused on analyzing the performance of double polling technique in the cross-country skiing athletes. So moving on, this is the outline which we'll be following throughout this presentation. First, we're going to be discussing the biomechanics of double polling and why did we choose double polling. Our selection of double polling has to do with the reason that it's the most commonly used technique across the skiing in the track, and also according to the data which we received, it was the most widely used technique. So from this, if we can speak of double polling, the biomechanics of double polling, we can see like starting with the the key parameters which we should rely upon in double polling is the pole plant, because it's a key feature which allow us to detect the start and ending of each double polling cycles. Some other parameters which we found that were highly relevant in the literature are mostly those kinematic parameters, which are cycle length, cycle rates, poles verticality, poles distances from the feet, joint angles and ranges of motions of them, and the angular velocities. And of course, for the balance assessment, we have to rely on center of mass. Mostly the distance from the feet was a very relevant parameter and very important one. Also, the vertical and horizontal displacement of the center of mass was very important. So for these previously mentioned parameters, we used to quantify the smoothness and the coordination of the movement and also the balance. And as we spoke before, the pole planting was a really critical point. So in order to accurately detect the event of pole planting, we relied on the shoulder flexion and also the pole's accelerations. So if you can see here in the animation, I don't know if it's working or not. Can you see it clearly, or is it on? Is the video on?
Yes.
Yeah, definitely visible.
Okay, that's good. So when you see the animation, you can see that at the moment the pole planting is occurring, you can see some perturbations in the pole acceleration, and at the same time it coincides with the peak flexion value in the shoulders. And so that's what we relied upon to determine the start and ending of each polling cycle. Each double polling cycle. So this required us actually to also reconstruct the whole kinematic structure and include as well the poles within the whole structure. And in order to fully analyze the double polling cycle, within the cycle, we need to divide it into between polling cycle and recovery phase. So these phases, the polling phase starts with the start of the double polling cycle and ends when the elbow flexion reaches the local minimum, which you can see here as well. If you look at the elbow flexion graph, you can see that once the subject is releasing their arms, the flexion reaches the local minimum. So this was a really important point for us in order to dissect our cycles. Moving on, we can, like some other important parameters were also the distance of the poles from the feet. And to do so, we also had to reconstruct and do some spatial mapping, and also to figure out the endpoint of the poles while the movement was being performed. and we relied on the kinematic data provided by the MVNX files in order to reconstruct it. So moving to the results which we achieved, here we try to present the most important ones. The kinematic parameters which we have found in the literature were really huge, the amount of parameters that has been used, but mostly they highlighted the cycle lengths, cycle rates, and some important points like the distances of the poles from the feed at pole plant. So we try to really summarize it in a really discrete way as much as we can. So by looking mainly at cycle lengths, we can see that, for example, P6, which was provided in the PDF files that was the elite performer, we can clearly say that he has the highest value, followed by P7, which was the advanced athlete, also had the nearest high value of cycle lengths. And following on with all the parameters, mostly they come in accordance with what we read in literature in terms of the performance criteria. For example, some ranges of motion were highly correlated with the good performance, which we have seen also here. Mostly P6 and P7 had similar aspects. So depending on these parameters, we try to also compare the unranked subjects, and so we can determine whether they are also elite, advanced, or any other ranking. And I guess in summary, we cannot just rely on kinematics results. That's why it's also important to just look at the power analysis and also look at the strategies adopted, which will be our friends, my friends are going to be following presenting this after this slide. So now we will move with my friend Yara. She will explain the power analysis.
Hello, everyone. Can you hear me and see me clearly? Yes, okay.
Yes.
So for the power analysis, there were many sources on the articles. Many of them use different methods, but not a single one was very concrete to be used or to be followed up on how to analyze specifically our data during cross-country skiing. So what we did was go back to the original point of what is power analysis. The fact that we need to find the forces on the joints and the angular velocities of the joints while the skiers were performing the skiing motions and techniques. So we went back and we thought, how can we extract that from the data that we have? And we found that from the MVNX data that we have, we can only get the angular velocities of the joints. So we have to find another way to get the moments or the torques applied on the joints and exerted by the skier. So we found a custom tool. It's called Custom. It's a toolbox in MATLAB, biomechanical tool, and we use it to calculate the inverse dynamics of the joints to get the joint forces and moments. We applied it with kinematic analysis. We converted the collected data to joint angles and segment positions using the custom toolbox. Then it's followed up by inverse dynamics. And then the mechanical power output that we have concluded was to be net joint moments times the angular velocities that we got from the MVNX data. And then we used this concept and we applied it on different recordings. First of all, we inspected the double polling. Since we focused it on double polling in our thesis, we took recordings, small recording sections from each participant doing hard round, and we took the double poll technique, and then we applied the mechanical power analysis on it. And we found out that since participant 6 is stated to be the elite one, then it should be the gold standard in which we compare different participants to him. We inspected participant 6 and we found that he has more synchronized power output between the upper and the lower body, that he managed to get higher power values and in a more synchronized way between upper and lower sections in order to get the movement properly right and propel himself forward in a high speed and high efficiency with the most balanced values. And then we found, after we mentioned in our report that we have ranked participant 12 based on many ranking stuff. We found that participant 12 was to be the next beginner, besides participant 3. And when we look at the power ratio between participant 6 and participant 12, we find that participant 12 seemed to have many noisy data, no coordination between upper and lower section. The synchronity is low, the power values are low. So in conclusion, this shows that the power exerted by participant 12 is lower than participant 6. And when we applied this analysis to all the participants, it helped us to reach a more concrete evidence to why we ranked the participants the way we ranked them at the end of our slides. Also, we have compared going uphill. We looked at the GPS data provided to us in the MVNX files, and we managed to track where the participants are going uphill. And then we took that section of the recording, and then we compared it between the participants in the hard round to see which of them exerted the most power. Even though we know that evidently by looking at the recordings, they have changed techniques. Some of them used offset V1, which is participant 13. Participant 12 used diagonal stride, and participant 6 used double polling. Even though that we can say that double polling is considered more of a speed technique other than a power, but he used it in a more synchronized or more efficient way, that when he propelled himself very explosive power and speed, he managed to get uphill very fast. And also participant 13, he shifted to offset, and he managed to use his upper and lower body in a very efficient way to propel himself upwards in a fast motion and higher values of power as well. While in participant 12, he took so much time to go uphill using diagonal stride, a very beginner based technique, safe to be used, but it takes so much time, low speed, low power to achieve this uphill reaching. We can see from the ratio, which indicates the most, that as I mentioned before, going uphill in participant 12 is more noisy and more it shows lack of synchrony, while in participant 6 we can see that synchrony. Also in 13 it's more closer to participant 6. We mentioned that we did a statistical analysis based on the mean and standard deviations of the techniques. We divided into cycles, and then based on the cycles that we divided from double polling, we managed to see that the mean and standard deviation of the power and the power ratio between all the subjects is what led us to conclude our ranking choice. And then followed up by aerodynamics.
I am going to have to ask you guys to wrap up because you're going a little bit over time. So can you keep this conclusion short?
Okay, of course.
Thank you.
Keep it really brief. We had to calculate the drag force, but in order to do that, we need to find the air density first. So we determined the air density using the ideal gas law and the barometric formula, which was found out by the weather reports. The skier's velocity was derived from the GPS data and the Xsense device recordings, and the drag coefficient was approximated as 1.21, depending on the body position and the clothing and the equipment. The frontal area was calculated with a custom-built MATLAB algorithm that would remove the background of the picture, and when given the subject's height, it would give an estimation of an area of 1 pixel. And that's how we concluded the amount of drag force they experienced. This is the parameters that we came across. Keep in mind, these parameters were calculated when the subject was directly against the wind, which will be explained in just a second. On the accuracy and limitations, the air density was mostly ignored due to the minor variations between each subject's drag course. And the drag coefficient, like I've said before, is an estimation based on typical values. Actual drag coefficient does vary, and wind tunnel tests and computational fluid dynamics simulations will provide more accurate values. On the frontal area part, inverse square laws effect was considered and minimized during the image process, but given the fact that the frontal areas were primarily considered, aerodynamic drag force was exclusively evaluated for the scenario in which the wind impinges onto the skier's front.
All right, you have 1 more minute.
Okay. Now on the adopted strategies and tracks, in all tracks, the beginners tend to rely more on the double polling technique with the occasional use of other techniques. For intermediates, a more diverse set of tactics is observed. Advanced skiers are consistently employ a combination of techniques, and elites mainly focus on 2 strategies across all tracks, indicating their high skill level in using these techniques effectively to achieve better performance. Thank you.
Okay, we're just gonna wrap up really quick. So we also did a classifier based on LSTM neural networks to predict the techniques rather than just label them manually, and we reached a 75% validation accuracy. Also for the friction coefficient part, I guess we don't have much time to go into details. We managed to get an approximation of the friction coefficient. And eventually, in conclusion, we can say that the kinematic analysis, although what's really good, the power and strategies were really necessary to come up with a good ranking strategy. And at the end, we come to the conclusion that the beginners were P3 and P12, P13, P14 were the intermediate, and the advanced P7 and P8, and eventually the elite ones were P6 and P5. And
all right. I'm sorry, I'm really going to have to cut you guys off. Thank you for your presentation. I would still like to give the room to the judges to ask 1 or maybe 2 questions, and then we'll have to move on to the next team.
Sure, I'm going to stop sharing now.
Thank you. Jury members, who has a question? Go ahead, Andrea.
I have a question. Thank you for your presentation. That was great. But I have some reservation on the power calculation, because you can see like there are big ups and downs, and the average is almost 0. I like it, the approach of the multi-body approach with the toolbox from MATLAB, but I have a reservation about the actual values, because you didn't take into account the external forces. Do you have any comments on that? And do you have any idea what kind of sensor would you need to complete the analysis with the external forces?
Yeah, actually, that's true. We couldn't really rely on external forces because we could have much input about it. Mainly, we have like wind speed, but we don't know anything about snow friction, which was like an optional part we were trying to calculate. But even though if we try to estimate it, it wouldn't be really accurate to just include it in the calculations of the power. So that's why we just relied on inertial parameters to compute the actual power of upper body and lower body. So it's just like the power was exerted only from within the body, not from the outside. I know it's like not enough, but that's what we managed to do, like depending on our resources.
Thank you.
Thanks. Thank you.
There's room for 1 more question. All right, then. Thank you so much, Biomechanics. I'll
thank you very much. I'm really sorry for exceeding the time limit.
No worries. Thanks, guys.
Okay. Thank you.
Next up is Team Salzburg with their title Cross Country Ski Main Report.
Thank you for inviting us to present today. We will do our best. With my colleague Lucas, we are both PhD students in sports science in Salzburg, Austria. And we will start right away presenting. So first of all, it was necessary to define a ski cycle, and we did it as the time in between 2 consecutive pole planes in double polling, the technique that we present today, where pole planes were identified as the peaks in linear acceleration from pole sensor, using as a useful reference the shoulder joint angle, provided that in double polling, peak flexion occurs in proximity of the pole plane, whether before or after. This said, we can go through the first class of metrics that we present, which are motion quality parameters, and we will see today in particular coordination variability and balance. Let's go for the former. Coordination variability was assessed based on angular velocity at 3 joint couplings that we consider relevant for double polling gestures, namely knee hip, hip shoulder, and trunk shoulder in the sagittal plane. So first of all, as we can see the picture, we have a velocity plot with each one trajectory being a single ski cycle. Next, at each time percentage, we fit around the pertinent data from all the trajectory and ellipses. And when we repeat the same process between 0 and 100% of the ski cycle, we obtain for each participant a time series with the ellipse area across the entire ski cycle. Importantly, a larger ellipse area indicates higher coordination variability. Let's see the results. Start with hip shoulder. The trend is identical for all the three couplings assessed. So we have participants 6, 5, and 13 showing the highest values of coordination variability, whereas the opposite is true on the bottom of the picture for participant 3 and participant 7. Trunk shoulder, same trend with same participant. And the same is true also for knee hip, with participant 5, 6, and 13 always showing higher values. We consider this relevant for performance since in several disciplines, such as, for instance, swimming and trail running, a higher coordination variability is considered a hallmark of more proficient athletes, since these subjects, so to speak, have at their disposal more movement solution to cope with an unpredictable external environment, such as, for instance, a ski track in our case. Conversely, a low coordination variability might possibly indicate a over-rigidity and a poorer motor adaptability, which are both detrimental for performance. Let's now see balance, which was calculated as the displacement of center of mass in the horizontal plane with respect to the mean point in between the feet, provided that in double polling, feet are supposed to be approximately parallel. Results are normalized to body height, so to make between subjects comparison sensical. Participants 6, 5, and 13 display the largest center of mass displacement, whereas on the bottom of the picture, the opposite is true for participant 12 and participant 3. This is relevant for performance since higher center of mass displacement is considered a key performance parameter in cross-country ski performance, provided that more proficient athletes tend to maximize the range of motion at their joints in order to ultimately optimize performance. And those were our motion quality metrics. I will now dive into power output, which was estimated based on the 15 segment models introduced by Norman and colleagues, where ski were modeled as parallelepipeds and all other body segments were approximated by cylinders. Length and weight of all body segments was estimated as percentage of body height and weight based on previous research. Thus, we were able to calculate at each segment the total mechanical energy as the sum of kinetic translational energy plus kinetic rotational plus potential energy. From physics, we know that in between two time points, the energy difference, equals the work, and dividing the work by time yields the power, and this was our approach. Let's go through the results. Top left, we have lower body power output with participants 6, 5, and 13 outperforming all the other skiers, both in absorbed and generated power, with participant 3 and 12 showing a relatively flat power output, whereas moving to top right picture, upper body output, what we can notice is that participant 6, the green line, outperforms clearly the rest of the athletes. Participant 5 and 13, in this case, perform well, but not so standingly, I would say, compared to the rest of the group. When comparing upper and lower body contribution, bottom picture, with 100% being upper body contribution only and 0% being lower contribution only, it's not actually possible to see any clear trend between athletes like in previous quantities. Nonetheless, it's interesting how different athletes choose a different moment of the ski cycle, earlier or later, to switch between upper and lower body. So this was power, and I will now hand over to Lucas.
Thanks, Matteo. I will present our results regarding strategy and pacing. First of all, let's focus on the finish time. Finish time is the most important and most obvious performance parameter in cross-country skiing because it's the only official performance measure in races. When we look at the finish time during the hard round, where participants gave all they had, we see a clear ranking. Participant 6 was the fastest, followed by 5 and 13, while participants 3 and 12 were way behind. But we did not only evaluate the total time, but also looked at the performance in different segments of the track. Based on the profile of the skiing track you see here, we defined 7 segments, characteristics, from flat, uphill, downhill, as well as a turn. And then we calculated the split times for each athlete based on the GNSS data. On the right, you see the time accumulation over the segments during the hard round. And it's clearly visible that the group divides into 2 packs, a fast and a slow pack. When we now look closer on the fast pack, we see that they again split up at 2 indications. So the first is the first flat segment where we see a little bit of a split up, but then in the turn, those 4 athletes split up even more, and this is then maintained until the end. The analysis of races like that, where we identify critical segments, is information that's very useful for coaches and athletes in racing. Next, we also looked at the sub-technique distribution during the hard rounds, and we put a special focus on the 2 uphill segments. Therefore, we first classified the used sub-techniques of the athletes using the avatar and the Accent software, and found the uphill techniques. When we look at the results, we see that only participants 5 and 6 maintained double polling sub-technique during all uphill sections, while all other participants switched at some point to a less powerful uphill technique. Sub-technique choice, of course, depends on different things like personal preferences and skill level, but in general, literature shows that successful skiers are able to maintain more powerful sub-techniques for uphill sections, and that's related to performance in elites. Lastly, the last parameter we looked at was the cycle length, and cycle length in the double polling cycle was calculated as the horizontal distance between the start and the end of each movement cycle, and this again has also shown to be strongly related to performance. And here we see the same trend, participant 6 outperforming the others, but followed close by 5, 7, and 13, while the median cycle length for 3 and 12 was only 5 to 6 meters. That brings us to the final ranking with the summary of all analyzed performance indicators. As you see here in green, we're indicating a good or a strong performance, yellow means neutral, and red represents a poor performance. And most of you would probably agree with our ranking that participant 6 takes the gold, 5 is the silver, and 13 is bronze. The other participants follow as you see here. That's it from our side. Thank you very much.
Thank you.
All right, thanks a lot for the presentation. I see some screens flicking on, so I guess there are some questions. Who'd like to start? Jeroen, can I give you the word?
Yes, sure. Thank you for your really nice double presentation. I liked it a lot. I have for the last speaker, I have a quick question. What there's obviously a clear indication in cycle lengths. And what I wonder about it is that the variability apparently in the cycle lengths, especially for the elite, is quite high. Could you comment on that? What do you think about that?
Yeah, I think it goes together with the previously mentioned result that he or she used also double polling in the uphill sections. And in uphill, of course, you have to push a lot faster or increase the frequency, and you won't glide so long. So therefore, we have a longer, shorter gliding time. So therefore, shorter cycle distance. And then also in the high speed of like flat or downhill, he is also probably still able to have very efficient double polling, while other participants might tend to glide or don't push so much.
Yeah. Okay. Oh, so the cycle length is for the whole loop, so to say, and it's not specific for one technique.
It's specific for double polling. Yeah.
Oh, so it is specific for double poling, even though it can be uphill or downhill.
Yeah,
it's
yeah.
not just double poling in the flat or double poling in the.
No, we
okay.
haven't made that difference. It's double poling during the hard round for all cycles that the participants use this technique.
Clear, thanks. One more, if I may ask.
Go ahead.
It's probably Matteo. Yeah, I think so. Did you use? Did you contribute or use the external forces for the power calculations?
We actually just took into account the total mechanical energy of the segment, so we didn't consider external force actually in our calculations.
Okay. Yeah, I vaguely remember there was something in your paper about it, but no, okay, I'm not sure anymore. That I have to check. Okay, thanks a lot. Thank you for your work presenting.
Thank you.
All right. Any other questions?
There was one question from the chat asking how we could identify the segments for those athletes whose RTK data were not available. I maybe can just provide the first explanation. Lucas, maybe if you want later add some details. So we had the RTK data from some athletes, and what we did was to identify, provided the 3D data for those participants for which these data were available. We identified the 2D latitude and longitude coordinates where the different segments started. And then Lucas projected this data, combined this data with the GNNS data, which were available instead for other participants.
Yeah, so basically we looked at the split points where we said, okay, the uphill starts here and ends here, took the coordinates, longitude, latitude, and then projected these on the trajectory of the GNSS data that was integrated in the XSense suite. And we defined the projection at the minimal horizontal distance of these two, of the point to the trajectory.
All right, thanks. Daniel.
Yeah, also thank you very much from my side for this nice presentation. Maybe I would just like to ask if you could recap your procedure to define the cycles or to get the cycles from the double polling. So you first looked at the XSense data and then cut out all the double polling trials or the segments, or did your algorithm already account for the different sub-techniques?
Well, first of all, we started with the shoulder flexion extension angle because it was a more regular trajectory compared to raw acceleration. And look at the avatar, we know that in double polling, by definition, pole plan occurs in proximity of the joint angle. Once that we identify the flexion peaks, we search in a appropriate time window before and after shoulder peak flexion. And we identified the acceleration peaks from the pole sensors within this time window. And this time window was tuned properly for each participant. So to recap, we started from joint angle, identified the flexion peaks, and then we took the data from the pole sensor. Based on the time frames of flexion peaks in the shoulder, we search before and after a certain time window. And then in our acceleration data, we were able to identify the peaks after filtering raw data.
Yeah. A quick comment on that, Daniel. We first, before we did any analysis, we looked at the XSense avatar and defined the segments where each sub-technique was used. So we first extracted the part where double polling was used, where diagonal was used, and so on, and then analyzed only double polling based on what Matteo just said.
Okay, I see. Thank you.
Yeah.
And then we're moving on to SkiSense Innovations. With their title, Automated Performance Ranking of Cross-Country Skiers Using Inertial Measurement Units. I'm going to add in Christina.
So, good afternoon. We are Team SkiSense Innovation, and we would like to thank Movella for hosting this Biomechanics Challenge, as well as the many people who were involved in the data collection and organization necessary to create such an opportunity. Today, we will present quantitative ways that XSense IMU system can be used for automating the performance evaluation of cross-country skiers. My name is Alex Moorhead. I have had the honor and pleasure of being the mentor to Cristina, Filippo, Andrea, and Rachele, all of which are finishing their postgraduate studies at Politecnico. Together, we are Ski Sense Innovation.
So there are two different classes of techniques, the classical and the skating. In this research, we decided to focus on the classical one, in particular on the double pull technique and during the hard round, where the participant was asked to go as fast as possible that, in our opinion, better represent the athlete's best performance. The case study is composed for the classification of the ski level based on the quantitative measurement. 8 athletes were acquired by X-Sense Link system and a GPS system while performing one cross-country ski track in 3 different conditions. One round at slow pace, one at medium pace, and the last with the maximum effort possible.
Using the RTK GNSS data provided for 2 subjects, we were able to differentiate each of the 4 loops performed, normalize them to the same length, and reconstruct the 3D approximation of the track performed by the athletes. We approximated the length to be equal to 783.26 meters, with a standard deviation of about 11 meters above across the whole trials. While the 3D models appear to display a large difference between the first and the second hills, the difference was actually only found to be around 1.75 meters, which we expected is partly due to the inclination of the track being situated on the hill. We also concentrated on observing which technique was chosen by the athletes while ascending the hills. Those who needed more balance, such as the beginners, would utilize the herringbone technique, as opposed to those who were more experienced and wanted to maintain a constant acceleration at a maximum speed with the double pole technique. Next slide.
Okay, so when evaluating the kinematics of the skiers, periodic signals were observed in flexion extension of both shoulder and knee joints. So given the high repeatability of the double pole technique, we decided to automatically divide into cycles using periods of the shoulder signal, thus identifying maximum peaks in the signal. Each cycle was then defined as 2 consecutive peaks, thus defining a complete flexion extension of the shoulder. By using the peaks identification, it was then possible to define the time instance through which the duration was computed as the time difference between the 2 consecutive peaks. Once each cycle was identified, the smoothness was defined as an indicator of the patient's capacity for selective motor control, as reported by the paper of Kaimi et al. And a more fluid movement is then related to a higher capacity in performing the given task. We expect, therefore, elite athletes to be smoother than beginners. We relied on the formula reported on the slide, which is based on computing the jerk, which is the third derivative of a positional signal, to quantify the peaks in the velocity of the movement. A smoother movement will then present fewer peaks, thus a lower value of smoothness corresponds to a better performance. The jerk has been then normalized by the duration and length of the movement, where the length has been defined as the range of motion of each joint angle, while the duration was the duration of each cycle. Finally, as an overall result, we obtained the median smoothness among all cycle smoothness as an overall total smoothness result.
Regarding coordination, to obtain a value associated to each athlete, a coordination index was defined as follows. Bimanual coordination was defined between the contralateral, or right and left side of the body, and the hand-foot coordination was measured between the upper and lower body joints, both ipsilaterally and contralaterally. Bimanual coordination was the mean value of the Spearman coefficient of the 4 different joints analyzed. Hand-foot coordination was the mean of time delay between the shoulder pulling movement and the knee full extension. And higher coordination index correspond to higher performances. While balance was not yet numerically quantified, it was closely related to both coordination and smoothness of movements. In fact, by observing a 3D trajectory of each athlete's center of mass during their trials, it can be seen that some athletes displaying much smoother and repeatable traces, particularly in the mediolateral displacement. In addition, when observing subject P3, there is a larger projection in the vertical plane due to them falling.
As third parameter, the track time of the hard round was computed and adjusted by increasing 11% the females one for comparison to the males. Next, the mean power output per stride was calculated as the mass of the subject multiplied by the 3D acceleration and the velocity of the center of mass in each frame across the duration of a cycle. Finally, to investigate the role of the upper and lower limbs, the acceleration of each limb's center of mass was computed as the sum of the single segments of the limb multiplied by their acceleration, all divided by the total mass of the limb. Overall rankings were decided according to the athlete's outcome in each category, multiplied by the weight of each category that is shown in the pie chart. In this way, the final ranking was decided according to the highest cumulative score, and thereby also assigning the experience level to the athletes whose level had not been provided.
The techniques used in this study are relevant not only in skiing, but many other sports for multiple reasons. First and foremost, it allows the clinician to evaluate the athlete in the field of play where they can perform real-life movements and encounter realistic challenges which they would encounter during their sport. Additionally, these analytical techniques allow clinicians to provide an objective evaluation of an athlete's performance far beyond the final time of the race. This allows the coach or clinician to focus on the exact parameters which need improvement rather than a subjective estimation of the athlete's weaknesses. Beyond the evaluation of skill of one athlete, it also allows athletes to be classified universally upon their skill level and may help identify developmental athletes while giving them a standard for which they can strive to train. Moreover, it would be important to evaluate all athletes periodically as it shows their progress through time, identifies potential injury risks, and gives them a concrete baseline for return to play protocols should they injure themselves. As presented, the results of this study confirm that the quantitative analysis of kinematic motion capture using the X-Sense Link system can be used to automate the objective evaluation of skill level in cross-country skiing athletes. Analysis has shown that athlete P6 was the most advanced, while P3 was the least skilled. While the balance was not yet factored into the final ranking, it was partly evaluated in both the coordination and the smoothness of movement. In further analysis, this will also be quantified and factored into the final ranking. Additionally, further investigation of the various techniques should also be performed. These methods can be easily utilized by clinicians everywhere to more accurately evaluate athlete performance and health. In future studies, these methods can also be applied to different sports and individuals. Thank you once again to Movella and everyone involved in organizing this challenge, as well as those watching and the jury panel. We'll be happy to take any questions regarding the presentation.
All right, thanks a lot for your presentation. I'd like to give the word to one of the jury members who has a question. Can you guys show April? You have a question.
Can you go back to your slide, please, of the performance score, that pie chart, and then how did you determine the weight of each category that would contribute to that overall parameter?
Oh, I can take this question. All right. All right. The different weights were given based both, let's say, theoretical thinking, because the track time, basically, if you arrive as first, usually you are the best athletes. So we gave to the track time the higher score, the higher weights. For the others, actually, it was given by the other ranking of the parameters that we also have in the slides, in 2 extra slides, and the weights was finally given by the fact that the best athletes. So, for example, the elite that we already knew that he was an elite. If the elite athlete had a greater score and a greater ranking in that single parameter, that parameter was given a higher weights, because that means that that parameter was actually good correlated to the athlete's level, and therefore we figured out that the acceleration of the limbs was highly correlated with the actual level of the athletes. Instead, the less correlated was the smoothness of the movement, because we saw that even the P3, according to our calculation, even the P3 athlete that is a beginner had a quite good smoothness index. No, sorry, P12. I said the wrong number. And so it was a theoretical, let's say, weight classification.
All right, thanks. Andrea, you have a question?
Yes, it's a more curiosity. I'm interested in like the derivation of the 3D track from GPS, and you showed like the GPS data, but on your graphs I could read like X and Y. So did you translate it from GPS units to ENU units, and how you did that? And just in case, can you put more color on
Yeah.
that, please?
Thanks for that question, Andrea. Actually, I took the GPS coordinates from the two subjects which were provided and reset everything to 0. And then by checking when the XY distance from the start was less than 1 meter, I actually was able to divide it into what turned out to be 4 cycles instead of 3, as each of those two subjects did 4 cycles. I'm assuming maybe one was a warm-up. Then using the 4 cycles of each of the subjects, I normalized across the shortest number of samples, and I resampled each of the data so that I could find a mean XYZ coordinate for each sample within that. And that was also using a factor able to translate, those are in actual meters. So it shows meters from start instead of longitude and latitude. If that
Thanks.
answers the question.
Thank you. Yes.
Okay.
Yes.
All right, any other questions?
Yeah, I would like to ask a question. Thank you for the nice presentation. As the first question, I wonder if you, in this pie plot that you made, if you don't use finish time or lap time, how would that affect your final score? Because finish time or track time is a little bit of an obvious one, obviously, since that's the end goal of cross country skiing. But for a coach, for instance, it would be very nice to he knows the track time. That's the easy part, but all the others are obviously very interesting to give as feedback to a coach. So could you do the same performance analysis but without track time? That's basically the question.
Yes. Basically, the track time was taken into account because we didn't think about only the coaching perspective, but all the other parameters actually were more or less, let's say, on the same page on the athletes level that we ranked. So the track time was taken into consideration, but even without the track time, more or less the ranking would stay the same. So even
sounds good.
Yeah, okay. Basically that's it.
Yeah, sounds good. That's cool. It's nice that you actually corrected for male and female. Thanks for that. Yeah.
All right, thanks. There's one more question from the audience that I'll allow, and then we have to go to the next. So Nicolo is asking, how come you calculated the power output using the acceleration and the velocity of the center of mass that are given with respect to the frame of reference centered under the pelvis?
Filippo, do you want me to take this?
Yeah.
So while the center of mass reference was given in respect to the pelvis, you can look at actually the 3D acceleration in every moment. And so I took the acceleration X, Y, and Z, as well as the velocity in X, Y, and Z, and was able to find a 3D projection. And so although it's the frame of reference is localized, you can still see the acceleration of the subject. And I often relate this to as though you were to measure somebody running on a treadmill. You don't need GPS data or anything like that to see the power output, and that would be the same with cyclists. So if you can look at the COM, the center of mass movement of somebody in a stationary position, by just looking at that deviation in the center of mass, you can use that. And I found it more easily calculated using the actual GPS, or pardon me, the center of mass data from the Movella, from the XSense system, since I think that was the objective. If that answers the question.
All right, thanks for the answer. If it doesn't answer, then Nicola will reach out for you. All right, thanks a lot. All right, and we're moving on to the MHM U20. So with their title, Classification of Cross-Country Skiers Based on Human Motion Tracking Sensors.
So welcome everyone, we are MHM U20 and we've been participating in the Movella Biomechanics Challenge as well. Yeah, let's skip straight to the next slide. We have created a model that combines two factors. The first one based on the power output of the skier, and the latter would be a smoothness parameter. And we will take you step by step through these parameters and their underlying assumptions and our initial output. Finally, we will finish with our conclusion and address the limitations of our model. So at the start, we made a guess based on the performance, for the performance rating based on the time. This is like the result. We can see that P3 and P12 are the beginners, and P13 and 14 intermediates, and P5, P7 and P8 advanced, and P6 as an athlete. So our main goal is a biomechanical model, and we've based it on an inertial reference frame with respect to the Earth, or at least we try to, but we have to make some assumptions under it. So first, the general power equation for a system, or a purely mechanical system of a non-rigid body, states that the sum of all powers of external forces and that all powers exerted by internal forces equals the rate of change in kinetic energy. And this is the formula shown at the top. So the external power, so the net forces of the forces acting on the skier, gravity, wind, and contact forces, which we will try to take into account. So with regard to the rate of change in kinetic energy, we know the acceleration of the center of mass, as this equals the center of mass acceleration relative to the pelvis, plus the free sensor pelvis acceleration given by the inertial measurement unit. Since everything is fixed to the pelvis in that data, we can use the free sensor acceleration to bind the data to our inertial reference frame. Thus, the only remaining unknown is the velocity of the center of mass. Given that we did not have any information or data about the mass displacements of any of the limbs, we could only estimate the right side of the equation with the mass times acceleration times the dot product of the velocity of the center of mass. So this is our underlying assumption. And thus we can then estimate the internal power as the difference between the rate of change in kinetic energy and the external power. So can you please go on to the next slide? In order to calculate the external power, we must sum the power exerted by all the external forces. And we know that these equal the dot product of the force vector and the velocity of its point of application. So our next task was to identify the external forces and the points of application. So using Newton's second law, we know that the sum of forces then equals the rate of change in linear momentum. So in our case, for this basic skier, we have modeled the external forces as gravity, the two contact forces at the skis, the two contact forces at the pole, and air friction. So it is clear that finding the velocity of the center of mass of the skier is paramount for estimating the power. Furthermore, it is also necessary, a necessary factor in determining the drag force of the skier. Since we determined that calculating the velocity based on acceleration of the center of mass suffers from integration drift, even after high-pass filtering, we must estimate the velocity of the skier. We used the GNSS data for it, and but that does limit our subjects to 6 out of the 8 because not everyone was equipped with the GNSS data suite. So this is plotted in a figure where you can see our estimation of the global GNSS data is roughly equal to the speed as calculated in the data by the GNSS RTK data. So with regards to the air force, we use a standard friction model for the air friction, and we use the box model frontal area of the skier because we didn't know any measurements of the human body we could make assumptions for it. The previous one made a nice model for this, but we just created a linear model which scaled on height and fixed width. We've also omitted the opposing wind power for simplicity, but still that resulted in some nice results, because now that we know, or we take the periods where the poles are off the ground, they're not in effect changing the linear momentum, we can calculate the force on the skis, or estimate, I would say, because this is the only remaining unknown external force according to our model. So this is shown in the right-hand side figure, where you can see the force in newtons for the skis is an estimation in the vector in 3 dimensions. So, like I previously mentioned, in order to calculate the external power, we must sum the forces with the dot product of the velocity of the points of application. So then what are its points of application? Well, for gravity and the air component, it's quite straightforward, but the point of application of the skis and the poles are harder to determine. We cannot estimate the inertial forces, nor the velocity of the point of application. So we assumed that the velocity of the point of application lies at the center of mass, which is going to turn out to be a bad case, but we will discuss that later. Technically, obtaining the exact points of application of all forces would require to solve the rotational equation of motion, or angular momentum balance equation, for the entire system, and this would again require a detailed model of the mass distribution of the subject. So, all in all,
I think we've lost Colin.
I also think that, but he was almost finished with his slide, so I will continue with.
All right, go ahead. Thank you.
Part after this. So I will talk about the smoothness of the signal. To determine the smoothness of a skier, we have looked at the amount of chaos in the signal. And if a signal is more smooth and periodic, there will be less chaos in the system. Before we could apply or calculate the stability or smoothness measure, we had to apply a filter with a cutoff frequency of 20 Hertz to reduce the noise. Then we calculated the harmonic ratio as a stability measure on the signal. The harmonic ratio is based upon harmonic theory to examine the symmetry within a stride by exploiting the periodicity of a signal. Therefore, the proportion of the base frequency within the internaty of a signal is calculated. This proportion is calculated for each round and each person in all 3 axes and the average of the axes per rounds, and consequently the average over all rounds is taken as the stability measure. For a smooth and periodic signal, this proportion will be greater, and therefore this ranking we have over here is sorted on the stability measure. In this ranking, the subject 6 has clearly the best stability, with subject 5, 7, and 12 are comparable, but subject 13 and 14 are definitely less stable. Then our discussion first of the biomechanical model. Unfortunately, our biomechanical model could not provide meaningful results. This could be due to an uncertainty in the kinetic energy change. We only considered the center of mass energy and velocity of the GPS data. And there's also probably an uncertainty in the individual forces and the points of applications, like Colin was already telling you. Then we still have some improvements for our model. First of all, there could be an improved estimation of the air friction. Therefore, we would need a better estimation of the frontal area of the subject. We now chose a fixed number for all the participants, but there was definitely there were not all the same height, so this is not correct, of course. And we did not incorporate the wind directions, which could also be a good improvement. Finding the power of the skier was difficult because we would need both an accurate measure of the kinetic energy changes of the skier, as well as the external forces on the skier and the velocities of their points of application. To distinguish between the upper and lower body power, a detailed model of the mass distribution would be necessary. in addition to kinematics being expressed in an inertial reference frame. We did not have that, so we made some assumptions for this. And another improvement for our model. Sorry. Okay, then we're at the stability measure. We did try another stability measure because at first we thought about the Lyapunov exponent, but this one was really inaccurate. We think this is due to the environment because in this situation there are a lot of perturbations from outside the system, and one cannot distinguish between those perturbations and the skier's own instability. Still, for the harmonic ratio, these outside perturbations will influence the results, but we do not have a better idea than measuring in the skiers in a controlled environment, which would be indoors, which was not possible, of course. So that was our presentation, and thank you, Movella, for hosting and organizing this challenge, and we're happy to answer questions.
All right, thanks, Marjolein. Shall I add Colin back in?
Yes, if his internet connection is working again.
Yeah, the blue screen of death, he said. All right, I'll give the word to the jury committee. Is there anyone who'd like to ask a question?
I have a question. Thank you guys for the presentation. I would like to know more details around like the smoothness factor that you adopted. Which kind of variable did you use for the calculation of the chaos, as you said? I missed that. What kind of variable
we use the harmonic ratio, which is based upon the periodicity of the signal. So you take you look at the base frequency of the signal, and you look at how many times that signal or those frequency goes back in the signal. And if it's more, then the signal is more periodic and therefore more smooth.
And what kind of signal you're talking about? What was the variable?
We're talking about the position data of both the position data and the acceleration data of the center of mass of the skiers in both the X, Y, and Z direction.
Okay.
We calculated the harmonic ratio on both, but I'm not sure if we eventually used the acceleration data or the position data.
Okay. You have an idea what is the most sensitive one for discriminating the skiers? Do you find any insights?
Well, I think the acceleration data has more would be better.
Okay. Thanks.
All right, thanks. Daniel, go ahead.
Yeah, thank you. Maybe if you could go back to your power calculation slide, I would like to ask. I mean, I really like that you took the dissipative forces into account. Yeah, right.
This one?
I just wonder if you took the direction into account. Like, I mean, I have to work against the forces or the air drag and so on. So, because I mean, you argued it well and everything.
Yeah,
we explain it, but
yeah. These vectors are all in 3D vectors, and because the acceleration is based on the inertial, or like we've calculated the acceleration of the center of mass is with respect to the Earth reference frame, we have thus calculated the we just Did that answer your question?
I think I missed some parts, but it's fine. Thank you.
All right, thanks. Any other questions?
Yeah. Yes. Thanks for the presentation. Although you got a blue screen. The blue line that it's just a quick question. This blue line that you have on the screen right now, on average, if I look at it, this suggested power is 0.
Yeah.
or does that have to do with the fact that there's something wrong with the calculations, as Marjolein suggested or told?
Yeah, so basically what happens, because the right side of the equation is the rate of change in kinetic energy, and because we've based all of our velocities, because we don't know their points of applications, on the center of mass, these factors are the same. So when we're comparing the sum of forces by the external forces, the power of the external forces, which are all forces times the velocity of center of mass, with the rate of change in kinetic energy, which is the mass times the acceleration times the center of mass times the velocity times the center of mass. So that would, if you would take the difference, then it would be zero mathematically. So like the right hand side is missing the rate of changes in kinetic energy of the limbs with respect to the center of mass. So if we were to have that, then it would be a better model for sure.
Okay, thanks.
The York Biomechanics team.
So good afternoon, everyone. We are a York Biomechanics team, and we'll be presenting our results on the York Movella Biomechanics Challenge. Just as every other team has suggested or mentioned, we were tasked with identifying the skill level of 4 unknown skiers. We are given data of 8 skiers, and we had to classify them based on techniques, balance, or kinematics, as well as power split. So today we would be talking about how we determine a ski cycle, classification and technique identification, classification based on balance, classification based on power split, and then concluding it with some clinical and commercial applications.
So for the cycle detection, what we did was we took the x direction of the left forearm's angular velocity, which is in the sagittal plane. We passed that through a 4th order Butterworth filter with a cutoff frequency of 1.5 hertz. You can see here the blue plot is the original signal. The orange plot is the filtered signal. We then detected the peaks on the orange signal and then superimposed them onto the blue signal. And between 2 red points is what we considered a cycle. Just a zoom in section over double polling for P6, you can see 10 cycles as a result of filtering and heat detection.
So using the ski cycles detected, the first thing we worked towards was technique identification, so that we can use the techniques to identify both for balance as well as power determination. So for technique identification, we use angular velocity of the left and right forearms. We did the L2 norm of the XYZ signal because from our analysis, that gave us a more pronounced peak in certain situations. Similarly, we use the L2 norm, the difference between the L2 norm between the right and left leg angular velocity for determining a kick, just to ensure that if the person is kicking by the right or left, it's just pronounced, and during a double polling or something, the noise doesn't get filtered through. So this is a graph for an elite skier of all the techniques they use during the entire ski course. So zooming into the double polling technique was determined by correlation between the right and left forearm. The left forearm has a blue signal and the right forearm has the red signal. Once a double polling cycle was detected, if you look at the angular velocity or the difference in angular velocity of the legs, we notice a spike, which is the presence of a kick within a double polling cycle. So we consider it as a double polling kick. And then if the angular velocities were an antiphase, we consider it as a diagonal stride. Diagonal stride was further split into herringbone or running diagonal stride by visual confirmation using what the span of the arms or the limbs cover. So using the different techniques done by each skier, we try to segregate them into different parts of the ski course, like turning, uphill, start, and overall percentage. So looking at a map of a ski course, for example, during a turn, a beginner used diagonal stride, whereas an elite skier used a double polling kick. During an uphill section, the beginner skier again used a lot of diagonal stride, whereas the elite skier used double polling to ensure that their power or the speed is kept constant or at its maximum. And if you look at an overall cycle, a beginner use a higher percentage of diagonal stride or herringbone or a non-double pole technique compared to an elite who stuck to double pole to ensure the best time is met. So based on the ski technique classification, we thought the P5 was an elite, P8 was advanced, P14 was intermediate, and P12 as a beginner.
So in terms of coordination of the movement, we looked at the left forearm position and right forearm position of the elite and beginner skier. So you can see circled in red, the elite skier has a much different kind of coordination and timing to the beginner. That's because their follow through and their motion is very different. We have a clip here just to show what an elite skier looks like, just as a reminder. So full motion from the top in front to top behind and returning. We also looked at the time difference between the cycles. So taking an average between 4 cycles of double poling, because double poling was present in all of the ability levels. So it was a good comparator. We found that elite skiers had a time of 0.84 seconds per cycle, whereas beginners had 1.55, I think it is. Moving on. We have the balance and smoothness. So we use this model on the right here. Instead of having the base created by the heel and toe of the right and left foot, we averaged the position of each of the feet and then only considered the movement of the center of mass in one axis perpendicular to the feet, because we assumed that the center of mass would always be above the kind of lateral motion of the feet, the lateral axis. We have a heat map here to show the position of the center of mass, so X, Y, and Z for the heat map. We can see for an elite skier, there's a lot of time spent lower down, a lower center of mass, potentially while they're double poling and they're bending their knees and loading. And as they push forward and pull themselves forward, there's a lot of time spent in that position. We also see that there's a left region of blue or lower and an orange region to the right, which we believe indicates the turning. So coming round a turn, all of the turns were right-hand turns. So you'd go low from your left side, high to your right side as you're pushing around the corners. And then just another representation of the center of mass. All the black plots are the feet IMUs, so the positions, and the red plot is the center of mass X and Y positions. And we can just see visually that the center of mass always stays within the bounds of the feet throughout the run. So here, just quickly, the yellow plots in each of these graphs are the center of mass coordinates. So the X position and then the Y position on the right too. And where the yellow graph, the yellow plot stays within the orange and blue plot, they are balanced. We're considering them balanced. And we can see for the beginner skier, there's more crossover points, which indicates more variability in technique, more errors, not as smooth performance compared to the elite skier in the bottom two graphs. And then the performance rankings based on balance and smoothness are as follows.
Then for the power calculations, it's split into two sets. We had whole body power, which standard power calculation, force times displacement over time. Displacement was taken only in the XY plane, and the height was assumed negligible over such a small change in time. The force was then broken further down into mass of the skier times the acceleration of the center of mass. The next set of power calculations were segment power, and each segment was composed of a translational component and a rotational component. The plot on the right shows the power values, the whole body power values, the difference between hard and easy round, weighted to mass, averaged over 8 cycles of double poling. See the difference between elites and beginners quite stark. And adding in P12 and P15 ranked P12 with beginner, P5 and 6 as elite. The intermediate and advanced were not so easy to discriminate between, but including the results of the other calculations, this is kind of how we classified the skiers, resulting in this final ranking of the skiers based on power. The asterisk over advanced means there was some, we weren't entirely sure about that.
So ending with some clinical and commercial applications. Clinically, we feel that these can be used for injury prevention, specifically based on the ski course, like even for a ski sport, for like classical skiing or jumping, if you know the correct techniques to use, we can prevent any injury, and can also be used for rehabilitation to bring them back after a serious injury. From a commercial point of view, we think this can be used for testing new equipment, for example, using the classical equipment currently available, comparing them to a new one to see how the performance varies, and also for performance improvement of athletes. So final ranking based on technique, balance and smoothness, power, and overall. The asterisk basically shows at what points or where we were not sure whether they fell into the intermediate, advanced, or where there was an overlap between different classes. The final ranking is similar to what we had for the technique, because based on the technique, which is basically the different techniques used in turning, uphill, as well as overall cycle, we found that this ranking fit the data provided to us. Some limitations which might affect our ranking, as you mentioned, there's a variation between the metrics used, which is smoothness, power, and technique. Also, the skis used can be a different factor. Not everyone uses a classical ski. Some use skating skis, which could affect how we are analyzing the results. And lastly, none of us have experience in skiing, so most of it were from scientific data and YouTube videos. Thank you.
All right, thank you for your presentation. Jury members, are there any questions? Jeroen, go ahead.
Yeah, thanks for the nice presentation. You mentioned that in the end that injury prevention is something that where this way of technique analysis is useful. Could you elaborate on that?
Yeah. So this was basic. While we did not find literature for classical skiing, we did look at literature for ski jumps, and a lot of biomechanical analysis is done on ski jumps, where the way you take off as well as where you land. For example, how much you bend your knees, or what your lateral displacement is, or those landing force on your ankle, the angles made by your ankles can affect whether you have a serious injury or not. And since cross-country skiing is quite a high endurance, where you have lots of high sprints with a limited break between them, you need a proper overall holistic training. So if you know what techniques can you use and what can actually affect your body, that can be used for injury prevention, like, for example, going uphill, diagonal stride, herringbone, double poling, maybe you can kind of learn or train more, so you kind of prevent injuries, which could be serious. Yeah.
Yeah, it would then suggest more like what is the fastest way to do it? More performance.
Best way, endurance-wise, best way to ensure you don't reach fatigue and stuff. Yeah.
Okay. Thanks.
No problem.
All right, thanks. Daniel?
Yeah, thanks a lot as well. Maybe just a short question. When you calculate or you compared the center of mass position with regard to the feet, did you distinguish between the different sub-techniques there, like double poling and diagonal stride, or was it all together?
So I focus purely on double poling because that was available in or visible in all of the athletes, in all of the data. So for ease of comparison, stuck to that technique.
And for a beginner, what would you see there then?
In comparison to an elite, you see that the center of mass doesn't vary as much. So it's more consistently in the middle, and that the extremes aren't as great. So for an elite athlete, the extremes aren't as great as a beginner. So a beginner might go off balance more often and more extreme off balance.
Mm-hmm. Okay, cool.
All right, thanks. Any other questions? Oh, there's one from the audience. In what reference frame do you define your power?
In what reference frame? Are you referring to the segment power or the whole body power?
I'd imagine it would be the reference frame of global versus body frame. But correct me or tell me if I'm wrong, Colin.
Sure.
I think body, because you're not using the free acceleration, right?
No.
So it would be everything related to the pelvis, I assume. Nah, mine could be 40.
It's the acceleration. I use the acceleration of the center of mass.
So I'm assuming it's.
Yeah, I'm not sure.
Sorry, yeah.
That is what I meant, he said. So locally, yes, I'd say that's local.
Yeah.
All right. Well, thank you all.
Thank you.
I will exclude you from this.
Oh, yeah. Okay. Thank you.
Bye.
Thank you. Bye-bye. Thanks.
And we'll now move on to the Kinetic crew with their prediction of performance in cross-country skiing athletes.
Hello, everyone. My name is Andres Garcia. We're Kinetic crew. We're a group of students based off Barcelona Tech. Can go to the next slide, please. Right, so feel free to peruse our outline here from as I take some time to thank the University of Trento and Movella for organizing the event this year, and to thank everyone who has participated, because it is your work that keeps this community alive, and that's brilliant. Next slide, please. So let's actually get started. I'm not going to waste much time here in the introductory part, because we all know what's going on. I think mainly for our group, the main takeaway for this event was the opportunity to see the potential value of biomechanics, particularly in cross-country skiing. This was not a field of application we're very familiar with. So it was nice to see a little bit of what the particular interests in the field were, and what sort of the limitations were, and maybe some specificity of what kinds of analysis would actually prove useful here. So next slide, please. Okay, in light of that, so what's our objective here? So as per the requirement of the challenge, we're focusing in producing some kind of set of metrics that we can use to analyze the performance of athletes in cross-country skiing. And that's the key objective, of course, although of course there's going to be some side objectives that are going to appear as we go along. For our analysis, we're going to make a standard distinction between kinematic analysis and dynamics analysis. So I'm going to leave you with my friend John Badia for some information on the former.
Okay, so from the motion of the participants, we calculated the following. The first is a metric for smoothness, for which we use this equation, which uses the jerk of the center of masses to assign a dimensionless score to the motion. The smoother the motion, the lower the score. This value was calculated each second and then averaged for the whole lap. The force generated by the wind was approximated using this formula. Here, Cx is a coefficient extracted from literature. Another indication was the distance from the head to the feet of each skier. And we also took into account the time it took for each athlete to complete the lap. Another indicator was the balance, which we evaluated using the torque generated by the ground reaction forces on the center of masses. Essentially, what we measured was the moment arm of the ground reaction force with respect to the center of masses on the coronal plane. In this picture, the blue spots are the feet, the green line is the direction of the ground reaction forces, the red dot is the center of masses, and the black line is the moment arm, which we then divided by the height of each skier in order to produce, again, a dimensionless parameter.
Right, so here's our take on the estimation of the slope profile. So this is a little bit of a change in gears, because this has nothing to do with the performance analysis. So for this, we used a fairly simple approach. What we did was we basically estimated the component of velocity of the center of mass in the vertical direction by means of the segment orientation of the foot. So if you take the segment orientation of the foot, you can more or less take it to be the angle of the incline of the slope of the track. And then by taking out the velocity of the center of mass, or at least a projection or so from the GPS over in the horizontal plane, you can then use basic trigonometry to get the vertical displacement. Then we integrate that over the duration of a particular course of the track, and with that you can get an estimation of the profile. Hannah, please, you can hit the button. There you go. You can see our result here. So because it's an integration-based approach, it is susceptible to drift quite a bit, but we can actually make usage of geometric constraints of the track, so we can more or less assume that the right side of the track and the left side of the track are going to be similar in height. And there's also secondary constraint in the fact that if you do a full loop of the track, you should pretty much get back to the same point. So you can use that to impose shifts on the latter parts of the trajectory to get something a little bit more amenable, as like we're seeing here. Okay, you can see here once again image of the track. To see there's some nice qualitative agreement between our result and the original image. If you hit again, Mohanad, see the image from the opposite side here from the top. So there's like a slow going down, then slope.
Yeah, the second method is the dynamic analysis. Here we estimated the ground action forces by extracting the kinematics data, considering the Newton's second law, as we can see here in the equation. And then we calculate the joint moments using the OpenSim software. Later on, we calculate the joint power calculation by multiply the joint moment by the joint velocity. As we can see in the plot here, like the difference, the power, the difference in the power between the lower limb and the upper one in the subject 3, and here we can see like there is a big difference, like the big difference in the power range. Sorry, the model we used is like have 37 degrees of freedom. Later on, we calculate the fraction coefficient by dividing the horizontal component of the ground action force over the vertical one. And also we use this application in order to just to get the result, where we only like read the data from OpenSim and also from Extensive software, and then we can get the result by clicking on this icon. Sorry. And for the performance assessment, we use this linear system, where P is to represent the level of the scalars. A1, A2, A3, and 4 are the parameter, the known parameter, the balance, smoothness, time, and also the range or the ratio of the power joint. X1, 2, and 3, 4 are the coefficient. So we created this matrix in MATLAB, and then we obtained the result. We used two different methods. The first one, we use the ratio of the joint power by the upper over the lower. The smoothness and balance have been used, calculated using the including the GPS data. Where the second method, we use the posture score instead of the ratio of the joint power, and the smoothness and balance have been calculated without the GPS data. For the result, for the method 1, we obtained that the subject 5 is a beginner one, and for the subject 12 is between intermediate and advanced. And the second method, we obtained that the subject 5 is intermediate advanced, subject 8 is elite, and the subject 12 is beginner intermediate, and the last subject is elite also. I would like just to leave a comment here that if we could have more experimental data, that means we can have more probability to get more accurate results.
So from this study, we were able to extract the following conclusions. The first is that the balance data was useful in determining the skier's level. In contrast, the smoothness, not so much. And as expected, the analysis yielded higher power in the lower limbs than in the upper limbs. And the ratio between the two was connected to the skill level of the skier. Finally, the regression analysis allowed us to work out which of the skiers were more experienced using the data available to us. When it comes to furthering this work, we believe that it could be improved by including the ski poles in the dynamic analysis, automating the analysis so people less familiar with this project could benefit from it, and lastly, use a larger sample size, which would improve the results, especially if it is large enough to enable the use of a neural network. Thank you for listening. We hope that you found this presentation interesting, and we'll now take any questions.
All right, very interesting, thanks. Jeroen, you have a question.
Yeah, thanks a lot for the presentation. I have two questions. If you, I like the idea of making a model, a regression model, whatever. That's quite cool. For that, you obviously have to know that all your parameters that you put in are at least ranking more or less in the right way. or going towards the same goal. And what I see in the weighing factors is that for instance, the balance is quite a high number, whereas the lap time or the total time is a negative number. Can you explain that? How do I have to look at that?
Well, I would say that it's mainly because, for instance, the balance moves in a range of values around 0.1, 0.2, and for the time, we are talking about how many seconds it takes to complete the lap. So the scales are different.
Yeah, and that's okay to compare them, but also that it's negative for velocity.
Yes,
right.
that
So
is because
the idea is if it takes like a longer time, we will understand that there's lower performance. Like higher speed is higher performance in this sense.
Yeah,
it makes sense. It will be inversely fine.
Yeah, definitely that makes sense. You it seems you use all of the data of a participant to do the calculations on, or do you use subsets of like the double polling technique, or do you, well, basically, do you differentiate between the different techniques, or is it all going into your model?
We extract some of the data, not all the data. I mean, for sure, we used for each participant, for each subject, like the data, but not the whole data, not the whole Excel data.
Yeah, and the same part in the track. Yeah.
Yes.
Okay. And
right. So for us, an important assumption for us was that the both foots were touching the ground, so that we could actually properly distribute the reaction forces. And so what we did was for each participant, we went in and looked for places where this assumption was reasonable to hold, and we used that as the
especially for diffraction, like where we suppose that there's no relation with the velocity, and both of the skiers are on the ground.
Yeah. Okay. Thank you very much.
All right. April, you had a question.
Yeah, you showed two methods to classify your athletes, but the results didn't agree. I think it was P5 on one of them was beginner, and P5 on the other one was intermediate to elite. What would your considerations be if you don't have more data available, or like kind of looking at it from the lens of a coach? How would I use this, since those are obviously very different ends of the spectrum using the same inputs, basically?
I mean, we do believe that with more experimental data, that we can have more possibility to get accurate result. So within like 7 or we have 8 subjects only. So to generate an algorithm, we need more data to be able to train this algorithm and get more accurate result.
I would like to add that with the current data, I think that a coach probably would benefit more from going not just looking at the final score, but at each score, and looking for similarities and differences between different known level athletes.
Right. So here, one big problem here is that with this data set, we don't have any way to validate. So we can say, for instance, that subject 5 is a beginner, but since we don't know actually what a coach will classify subject 5 as, then there's no way to know whether this method 1 is better than method 2, or which one will take to be more credible. Because this is a simple regression of 4 parameters on 4 known values, then our methods are going to perfectly replicate the levels of the 4 known subjects, but for the unknown subjects, we don't know. This is a proposal, so this will be a construct that potentially models the level of performance of an athlete, and it will have to validate it, or if we have more information, we could refine the construct by seeing which variables actually correlate better, maybe exclude some, maybe add others, and so on.
And I would like just to add one thing. We use the linear system. So I think with the neural network, we can use, or we can get non-neural relation. So it's gonna be more accurate. So we can add more data or more parameter in the calculation.
All right, thanks. One last question, Daniel or Andrea.
Yes, I might have a question, Daniel, if you allow me. I'm really impressed and to see like an OpenSim implementation. I have like a question about like the ground reaction forces and the wind force. First of all, the wind force was applied to the center of mass, like in the OpenSim implementation, and about the ground reaction forces, because I can see like one term in your equation, so there is no distinction between the 2 feet. So did you balance the forces? So based on your assumption that both feet were touching the ground, you balanced these reaction
Yes.
forces, so some was going in one foot and some in the other, and then you took like the 3D direction and you applied that in the OpenSim model. Is that correct?
What we did, like the hypothesis was like both the skis are on the ground, the vertical and the medial lateral force are split like equally on between both feet. That's the assumption we applied.
Correct. And then you have like the forward direction is taken like same for both feet, I guess. And then
Yes,
the
both
wind.
feet.
Okay, and the wind force is like applied in the center of mass.
No, the wind force is like applied directly to the torso of the subject.
All right, yeah, torso segment. That's true.
Yes.
Okay, interesting. Thanks.
All right, thank you guys.
Thank you. Thank you.
Finally, our last contestant and last presenter of the evening is Team Brockworth Filter from Brock Biomechanics.
Okay, so hello and welcome to our presentation. We are Team Brockworth Filter and we're from Niagara, Ontario, Canada. Without further ado, let's begin our presentation on our user-friendly and practical automated coaching tool. So to begin, let's review the objectives of our work. Our primary objective was to generate a data-driven framework that allows us to evaluate discrete types of propulsion strategies in cross-country skiers across participants of differing and undefined skill levels. Our secondary objective was to develop an automated coaching tool that can depict differences in strategic and mechanical approach from beginner to elite level athletes. So for data acquisition, the collection was completed for 3 trials of increasing intensity and provided by Movella in conjunction with Trento University. And collection used the XSense MVN link system, and data from 8 participants were shared in analysis. We used 3 main strategies for our primary analysis. So step 1 was to complete a 3D reconstruction of the ski course that the participants used. Step 2 was to execute our principal component analysis for data reduction. And then step 3 was to classify the propulsion strategies and input them into our support vector machine. So if you look at the bottom left here, it represents the raw positional data we had when we initially plotted it in MATLAB. This was based on the XY positional data and the elevation from sea level data that we were provided. We can see there was some pretty significant drift in the blue colored lap data. Once we fixed it with cycle segmentation and drift correction, we were able to produce the bottom right figure for P13. So to correct, we segmented the laps using XY position around the track, and we removed the spatial mean for each lap to overlay it all together.
So for our pre-processing, our first step was a computation of joint power. So body weight and heights for each participant was inputted into Visual 3D software, where it computes limb lengths and masses based on its anthropometric databases. In doing this, participants were reconstructed in Visual 3D, and joint power was computed based on these estimations using joint angle and joint torques. Our second step was to align 3D coordinate data. So every frame had a local coordinate system built for the pelvis, and then we applied a transformational matrix relative to the global coordinate system of the position data. Our third step was to segment the strides. So one segment of the stride was constructed using the relative left toe maximal peak distance in Euclidean X, Y, and Z. So the stride begins when the toe is furthest forward and ends once it returns to the furthest maximal distance forward again. And we chose the toe because it's the most consistent component throughout all trials and all skiers. Finally, we performed a principal component analysis with the goal of reducing the data, thus providing coaches and athletes with functionally relevant information.
So initially, we based skill level on performance time, and our results revealed that participants 3 and 12 were beginner, 13 and 14 were intermediate, and 7 and 8 were advanced, and 5 and 6 were elite skill level. So the ones highlighted are the ones assigned by our team. Violin plots were used to visualize the distribution of the data, and unlike box plots that can only show summary statistics, violin plots depicted summary statistics such as mean and median, as well as the density of each variable. And although differences in segment time distributions existed, mean segment time between skill levels had minimal variance. So these results demonstrate that cadence is not the sole contributor of performance, and further analysis regarding spatial temporal coordination is required. So we generated a principal component analysis and violin plots to analytically investigate these skill rankings. The kinetic data collected for each participant was normalized and scaled so that the movement patterns of all participants throughout all trials could be pooled into one comprehensive database for analysis. If you look at the equation, all the rows correspond to individual segment movements, and all the columns correspond to time normalized time, XYZ coordinates, and scalar power time series data. So the database was then implemented into a PCA to decompose the complex whole body motion patterns of skiing into movement features correlated to skill, also known as principal components or PCs. PC scores were then assigned to each PC to explain a cumulative variance of about 90% within the data, which was retained for further ANOVA statistical analysis to assess the differences. Then multi-component reconstruction was generated from the PCs to animate the primary modes of variation present within the dataset that were systematically and significantly related to athletic skill level. The 5th and 95th percentile of each PC was exhausted to really exaggerate the different features of the different skill levels. And overall, this provides us with movement quality recording, character animations, and musculoskeletal modeling, allowing easy interpretation of skill levels for athletes and coaches alike. For the assessment of smoothness of movement, coordination, and balance, the kinematic data being assessed included the first 17 PCs, which explained a cumulative variance of 90.4% in the pre-processed dataset, as demonstrated in the scree plot in the top left corner and also the table at the bottom. Based on a systematic and statistical significance, PCs 4, 6, 10, and 11 demonstrate correlation with skill level. So in the top right corner is a violin plot of PC 10, and initially through multi-dimensional time-varying animations of single component reconstructions of each PC, we were able to interpret that PC 10 demonstrated features of ski angle and upper body effort, where the beginner skier shows increased angle and more wind up with arms to produce the same amount of power. This change through the skill level is seen through a systematic stepwise effect in the violin plot, and this interpretation can all be seen and understood easily with visually animated tools such as the next slide.
So the top two figures presented here display a sagittal view and frontal view of the multi-component reconstructions. So this is something that would be provided to coaches to allow them to give objective feedback to athletes in a more user-friendly way. So as indicated in these plots, the black lines represent the mean, the blue is the elite, and the red is the beginner athletes. So as you can see in the top right plot, the legs of the elite athlete tend to overlap a little bit, which is likely due to the insufficient variance within the data. And with some retraining and additional data, this animation could be improved. But nonetheless, this multi-component reconstruction can be used as a template to overlay real-time athlete data to essentially compare a selected athlete to the elite in order to assess different components which are presented below. So the frontal area and ski angles are presented on the bottom two left plots, where elite skiers tend to have both a smaller frontal area and ski angle, which helps to decrease drag and make them more aerodynamic than their beginner counterparts. So then the figures on the bottom right indicate that elite athletes tend to generate a greater upper body and lower body power, which is represented here by the shoulder, the arch or waist joint, as well as the knees when compared to beginners. So this falls in line with some of our findings that will be presented later on, but essentially the end goal is to make an automated coaching tool that can represent multidimensional changes, and this can be conveyed to a player or a coach for action.
So for the propulsion strategy classification, we decided to manually label a subset of segments based on a reconstruction of the striated sagittal and frontal plane. Since there wasn't very many examples of skating data, we decided to group all skating techniques together. Then we used a machine learning model to predict the classification of the rest techniques based on the segments that we manually labeled. We decided in using a support vector machine, which creates a hyperplane of best fit in multidimensional space to classify the segments shown in the bottom left. We ended up reaching 84% accuracy, and the AUC statistic in the bottom right was 0.94, suggesting a very strong model. So to display these results, we create a stacked bar graph which groups each skill level of the skiers together and shows which propulsion strategies that they use most frequently. We found that as the skill level increased, so did the frequency of the double pole technique, and there was also a decrease in diagonal stride with increasing skill level. And this also validates our findings regarding power production in the upper and lower body.
So essentially, this automated coaching tool has the potential to improve our ability to train and objectively benchmark technique, which will demonstrate the intersecting performance influences of frontal area, ski angle, and as well as power. So this tool has the potential to categorize propulsion techniques across the skill spectrum, which it can allow coaches to maximize performance. So some future directions of this project that our team would love to take would be to obtain some more data to allow for further analysis of propulsion technique interactions by skill as well as track location. With additional training, we could also improve the accuracy of our predictive classification model from 84%. And in addition, a third goal we would love to investigate would be the interactions between external factors on ski performance, like anthropometrics, mechanical properties of ski poles, and the effects of drag from loose fitting ski attire.
Thank you very much.
All right, thank you very much. Andrea, you have a question.
Yes, thank you guys for the presentation. That was very nice. I have a question. Usually when we adopt like a dimensionality reduction techniques, we also come up with some advice on the minimum amount of sensors that you can use to get the same results. Do you have like any advice on the minimum set of sensors that we would need to apply your technique?
Yeah, so we would just need a PCA, which just requires a lot of data. So ideally we would have at least, I'd say, more than 3 or 4. Ideally we'd have one of each segment so that we can have a large enough amount of data in order to get that high dimensionality to low dimensionality.
But is there any sensor that you would exclude from the setup to get like the first couple of PCA that can provide you with the accuracy that you need? So you just cut off them and you use only the information coming from few sensors and not all the sensors.
Yeah, so we might not need, let's say, the head sensors. Those ones aren't as important as, let's say, the arms and the leg sensors, the toe sensors. Those are really important because they show that large variation. The head sensors, it doesn't show any variation in their movement. It doesn't show any of their techniques in the movement. It wouldn't really help towards the PCA. We wouldn't need it for the PCs. The head one.
Okay, thanks.
All right, Daniel?
Yeah, thank you. Really great work as well. And I also like the approach of the PCA because I tried to apply it myself once. And so I maybe have some, or quite a lot of questions, methodically.
Reach out to us afterwards.
I hope it's okay. Sorry for that. Yeah. So, I mean, did you use, or the input was the coordinates and the power as well. So did you, apply it for the different units, or did you use any weights or so?
Sorry, can you repeat that question? It's cut out.
Okay. So when you're looking at the input to the PCA, the input matrix, we used coordinates and power data. Did you apply for the different units and using some weights or the normalization?
So we scaled it initially into one database so that it would be a comprehensive database. We could just put it into that PCA. We did scale it to start.
Okay, and for the reconstruction then, did you also use the power data or just the?
Yeah, we used the power data. We used all the data available.
Okay. And maybe finally, looking at the outcome or the video, what would you actually say to a beginner or a young athlete? How or what should he or she focus on to get to the next level?
So essentially, what this is doing, so I know a lot of sporting organizations, stuff like that, because the XN system is so expensive, we can essentially apply this as like a template where, because they're so expensive and maybe not everyone has access to these sensors, we can have a video analysis that would play beside it. So you could have like a video recording of it. And essentially, because the blue is the elite, you can essentially look and try and decrease your frontal area and maybe try and decrease your ski angle and try to adopt the other techniques we talk about later. But essentially you'd be able to, I guess it's like a whole knowledge translation thing where you'd be able to play like a video beside these videos, probably more in the sagittal view, only because a frontal view would be very hard to take a video of like a beginner athlete actually doing it. But essentially you could play like a video analysis beside this.
We actually
Okay.
have integration of video possibilities.
Yeah, cool. Thank you.
April, do you have a question?
Yeah, I have a new one now that this slide is back up. Why is the ski angle, the second graph there, the mean, why is that near 0, but the elite and beginner are 20 and 30?
So that's because within the PCA, once we put it into the multi-component reconstruction, we did exaggerate those 5th and 95th percentile just to show that like technical difference between beginner and elite. If we didn't exaggerate them, the mean would be in the middle.
And then goes along with the previous question. You mentioned during your presentation that this is like can be used in real time. How real time is it? Like, what are the feeds going into it? Like, as soon as Carmen does her lap, like as soon as she crosses the finish line, do I get this data, or what would be the lag there?
The lag would essentially just be like you would obviously have to like take it and input it. But it would be a lot more user friendly where you obviously would not have to wait like weeks and weeks and weeks in order to have this feedback.
It would be within like, let's say 30 minutes, an hour max.
Because essentially you could play this prior to like a practice or like training sessions in order to visually see something before you go out and actually try and do it.
But to that point though, a coach or even an athlete who's not familiar with frontal area or shoulder power, like how can you make a tool like this, like aside from adding a video, like more digestible to them?
I think one of the really good things to note about this is that you can kind of make it part of like testing is a really important part of periodization in any training model. And one of the great things about using this multi-component reconstruction is you can sort of see how performance changes over time for the athlete. So basically for any new trials, as long as you process the data and then add it into the multi-component reconstruction, you can kind of see the way that their process and their progress is being tracked over time. And then at the same time, you can compare to, like we talked about before, the elite level athlete and the beginner level athlete to see sort of what their attributes are more similar to and how different training techniques can change their actual physical manifestations.
Also, none of us are actual skiing coaches, so we can't realistically pair it with those techniques. If we could work with, let's say, a skiing coach, a sports performance coach, and we tell them an increased ski angle occurs in beginners, let's work with them and use their terminology to implement it to ours. So let's say then we put in the data from the athlete into our system. It implements these graphs along with that technical jargon that the ski instructor would have provided us if we were able to work with one.
All right, thanks. I see Jeroen still has a question, and there's one from the audience, and I'll allow for those, and then we'll wrap it up. Jeroen, go ahead.
Yeah, thanks for the nice presentation. Really cool that you use PCA for this and got this model to work on a beginner and an elite. I wonder, what is the benefit of putting power in your PCA calculations? And another question, could you leave it out and would that give similar results, or does that really hamper the output?
Yeah, so we only have 8 participants. So without the power data, that's not enough data to put into a PCA. It wouldn't provide us any realistic or appropriate information in the end in results. With the power data, we were able to get more realistic results. If we had a larger sample size, if we had, let's say, 100 athletes, we could take out that power, no problem, and do it separately.
Okay, yeah, that does make sense. Does it mean, but since the power is calculated from the coordinates, right? So it's not in some sort of a way a sort of double thing that you put in your PCA?
Sorry,
you understand what I mean?
No.
You use the you use the coordinates of all the joints and all the segments.
Oh, so
but that's also, yeah.
Sorry, no, I'll let you finish. Sorry. I thought you were finished.
Yep, no, it's fine. Thank you.
So,
go ahead.
Okay, so essentially when we did our power analysis in Visual 3D by C-Motion, we looked at specific joints. So we didn't actually look at like whole upper body power and whole lower body power. We essentially, for the upper body, we used the shoulders because those are the big driving factors of the double pull technique and a few of the other ones. and we use the RTA and the knee joints in order to look at the lower body. So we use those specific joint angles and joint torques in order to get the actual joint power. So we didn't actually look at like whole body power together.
Okay, yeah, I understand. Thanks. Thanks.
All right, then finally from the audience, Alex Moorhead has a question. While the automated coaching tool is certainly intriguing to look at, it seems somewhat complex for someone unfamiliar with data analysis. Can you explain how a coach or player could easily understand and interpret the animation?
Yeah, so I think this is a great question, but it's kind of related to what we were talking about before, where I think the model is a tool, not necessarily to be used by the coach directly. It's more of a knowledge translation tool where once you input data and process it, you're able to kind of compare your athlete's data to the data contained within the model. And that way you can make sort of comparisons between the data you have and the data that's contained within the model. So you can translate how your athlete sort of compares in different areas to higher and lower caliber athletes. And like I said before, I think it's also a great tool to track progress over time. So you can see comparing athletes to the version of themselves from a month ago or the version of themselves from 3 months ago. And you can see sort of how your training model is actually manifesting in real life, in real time, how it's sort of increasing performance over time.
Also, if you take our animations that are created from those multi-component reconstructions and you put a video of your athlete exactly beside it, you can show the athlete exactly on their screen. Look at the expert in our data analysis, how he has less frontal area. Look at your video and see how wide open you are. And that's how either the biomechanics team or a coach could take that and kind of explain it to the athlete.
To add to that, it's a little bit more difficult for, I guess, people that don't have that necessarily knowledge background on how to read a table or how to read like statistical analysis based on like just numbers. So we find that putting it in a more visual format just would help everybody understand a little bit better for people that don't have that prior knowledge.
All right, Alex says, okay, thank you very much. I certainly agree with the longitudinal tracking and adding video recordings. Great application.
Thank you.
All right. Thanks, guys, for joining. Thanks a lot. You were the last ones. So that also concludes these finals. I want to thank everyone so much for all their work and all their dedication, and now for all these nice presentations. You've really made a really, really nice job of it.